working on my PhD over in College Park. My advisor, Dr. Rupal Tour, normally gives this talk, but he is actually on sabbatical this year. He's at the Global Phosphorus Institute in Morocco. He's working there. So he asked some other folks in our lab to step in for him this year. So I'm going to be talking to today about nitrogen and phosphorus, and then we have some other folks from our lab tomorrow talking about sulfur, potassium, and soil and manure sampling. Yeah, so I'll just get right into it. I like to start out with this chart of all of the different essential plant nutrients ranked by how much the plants need of each one. And you can see on the top are all the micronutrients that the plants need relatively less of, and then you get into the macronutrients down here. And all the way at the bottom, we have nitrogen, which is the big one, which is one of the reasons why we talk so much about nitrogen in plant nutrition and soil fertility. So for every 1 atom of molybdenum the plant needs, it needs 1 million atoms of nitrogen. So you need a lot of nitrogen. And phosphorus is up there too. We'll talk about that second. I'm going to start off with nitrogen. So we need a lot of nitrogen. That's one reason why we are going to talk a lot about it. Another reason is that it's extremely dynamic. It's by far the most interesting of all of the plant nutrients. It has all these different forms. The forms are always changing around between one another, and a lot of those reactions are driven by the biology in the soil. So it's just super interesting to study. I study nitrogen. I think it's really cool. It does also make it a little bit harder to manage, but yeah, hopefully that gives us opportunities to improve, and there's always more to learn about nitrogen. And just as kind of a starting point, a reference point, most of the nitrogen on Earth is found in our atmosphere. It's actually found as a gas. So most of what you are breathing in with every breath is nitrogen. It's in a form that you can't use. Yes, okay. So most of the nitrogen on Earth is in the atmosphere, and most of the atmosphere is nitrogen. That makes sense. Okay. So just an overview of what we're going to talk about with nitrogen. I'm going to kind of give you an overview of the nitrogen cycle, which is how we refer to all those different forms and changes and all the different things that can happen with nitrogen on Earth. And we'll kind of zoom in on some of those different processes, and then talk about how carbon fits into that. I know Nia already talked a little bit about that. And then we'll talk about reducing nitrogen losses and ways to think about minimizing that. Okay, so don't be intimidated. This is the nitrogen cycle, but we're going to break it down into all the different pieces. It's actually not as complicated as it looks, and you probably already know a lot of this stuff already. So just to call your attention to the different colors, the blue boxes are the different forms of nitrogen. These are the 4 main relevant forms. There's other ones, but these are the ones that you want to know about. So again, I mentioned most of it is in the atmosphere, in the air, as N2, that's 2 nitrogen atoms bonded together. And then in the soil, we have these 3 different forms: organic nitrogen, ammonium, and nitrate. And the white boxes are all of the different processes where the nitrogen is moving around between those different forms. And then the green boxes are the different ways that nitrogen can leave the field. And we'll talk more about all these different things. So I'm going to start first with nitrogen fixation. And this is the process by which nitrogen is taken out of the air and transformed into forms that life can use. Because when it's in the air, it's in this super stable triple bond, and no one can use it. So there's several different ways that that bond can be broken. Because it's such a strong bond, it requires a huge input of energy to break. So one of the ways that it can be broken is with lightning. Lightning actually fixes small amounts of nitrogen that then fall to the earth. It also happens as a side effect of fossil fuel combustion. And then we have invented this industrial process called Haber-Bosch, you've probably heard of that, which is how most nitrogen fertilizer is created. And then amazingly, we also have bacteria that can do this, which is pretty incredible. This includes both free-living bacteria that can live in the soil and in water, and it also includes symbiotic bacteria that live together with plants, and they live in this symbiotic relationship, meaning they help each other out. So the plant gives the bacteria sugars as food, and the bacteria fix the nitrogen and give that to the plant, so they kind of live together. And of course, you are familiar with that with leguminous plants, soybeans and alfalfa. It can also happen in other plants, but that's the big one. And to talk a little bit about the scale of biological nitrogen fixation. Soybeans and alfalfa can fix pretty amazing amounts of nitrogen. So if you look at the pounds per acre that you can get from those two crops, like that's a significant amount of nitrogen, which is pretty cool. And of course, a lot of that is going to be harvested in your crop, but a lot of it will also be left behind in the roots and in any residue that you leave on the field. And so yeah, that's just something to keep in mind when you get into writing nutrient management plans, accounting for that leftover nitrogen that those legumes brought into your field for free. And there's more information about how to do that kind of crediting in the nutrient management handbook. Okay, so I just wanted to mention briefly just about the Haber-Bosch process, because I think it had like a really profound effect on human civilization, and it's worth just like taking a moment to appreciate that. So, so this chart shows you on the top line the human population over time, and then the next line below that, the pink line, is the total amount of fixed nitrogen on Earth. And then you can see below that there's a green line, that's the nitrogen fixed by the Haber-Bosch process. And you can see Haber-Bosch has dramatically increased the amount of fixed nitrogen on Earth, which has basically enabled the human population to be what it is today. And I think I've heard it said that like half of the people on Earth today would not be here without Haber-Bosch nitrogen. So it's pretty incredible. Of course, it's also had a few negative side effects that we'll talk about later, but yeah, it's just it's pretty cool. And yeah, there's a great book about the history of nitrogen and the lives of Fritz Haber and Carl Bosch, which I totally recommend if you're into history at all. You can talk to me afterwards. I'll tell you about it. If you're a history buff, it's like an amazing story. Okay, so let me just actually go back. So we talked about nitrogen fixation, and these different pathways are how we get nitrogen out of the air and put it into the soil. So once it gets into the soil, we're going to talk about how it moves around between these three forms: organic, ammonium, and nitrate. So among those three soil pools, organic is the big one. It's literally big here. And the organic nitrogen pool is a lot smaller. So what happens is microbes are going to break down this organic nitrogen, and they're going to release inorganic nitrogen into the soil pool in the form of ammonium, which will then later be transformed into nitrate. It can also go in reverse, where microbes take up the free nitrogen and turn it into organic nitrogen, which is less good if you're wanting that for your crops. But these processes are both happening all the time, constantly cycling. One may be more dominant at a certain time than another, but they're both always happening. This is just sort of a review of what I was just saying. Mineralization is the conversion of organic to inorganic. And then immobilization is the opposite. And these are both entirely driven by the biology in soil. Then we're going to talk about nitrification, which is when ammonium is transformed into nitrate. And this is another biologically driven reaction. It's a little different because it's very specific kinds of bacteria that do this reaction, and it happens in 2 phases. So you don't need to, don't worry, you don't need to know this equation. But the point is that there's 2 steps that they are done by 2 different kinds of bacteria. Normally in a well-aerated soil, they both happen sequentially quite rapidly. So as soon as the first one happens, the second one happens. So you don't really have to worry about this intermediate product, nitrite, that's formed. In some situations, you can have buildups of nitrite, like if the oxygenation of the soil changes, like if it rains and suddenly the soil is saturated, then you might get an accumulation of nitrate for a while, but normally it's not a big concern. Another thing to point out here, also that Nia mentioned earlier, is that the first reaction produces these hydrogen atoms as part of the reaction, and that contributes to acidifying the soil. So again, if you are using a ammonium-based fertilizer, that's going to accelerate the acidification that's going on in your soil. Yeah, so, and because all of these processes are driven by microbes, they're really dependent on what's kind of going on in the environment. So things will affect them like temperature and moisture and pH in the soil. Temperature is a really big one. So just like plants, microbes they're not super active when it's really cold. So during the winter, microbial activity slows way down or even stops. You can see on here, like below 40 basically are not going to have any mineralization or nitrification or anything going on. And then once it warms up to about 70, just like for plants, the microbes start getting going. And also just like for plants, microbes have certain levels of water and oxygen that they need. So they kind of like a 50-50 mix. That's the optimal. If they don't have enough water down at this end, the nitrification rate will be really slow. Then it goes up as you approach kind of 50-50. And then as you get too much water, the nitrification rate will again start to decline because there's not enough oxygen. And once you get really saturated, then you start getting denitrification, which I'll talk about in a minute. Okay, so that's a little bit about mineralization, immobilization, nitrification. So I'm going to talk next about carbon, and I'll make this fast since we have kind of already talked about this. So you add organic forms of nitrogen, meaning that they are coming with carbon. Yeah, she kind of already talked about this, but you do want to think about the amount of carbon relative to the amount of nitrogen. If you have a lot of carbon relative to nitrogen, you're going to get a lot of immobilization, and vice versa. So here's kind of what that looks like in a chart form. So if you add a high C to N ratio material, as the microbes break it down over time, they're going to suck up all of that available nitrogen that's in the soil, and there's going to be this period of time where there's like no available nitrogen. And then eventually you'll be released again as the microbes themselves die and break down. But there's this period in between where there's like really little nitrogen. So you just want to make sure that you're not, that's that's not when your crop is in the vegetative phase. And yeah, probably less of a concern for a large scale farmer, but very relevant in garden and smaller scale settings where people have especially wood-based amendments. So here's a chart of different carbon and nitrogen ratios. Anything with wood is really, really high. So like wood chips and sawdust are really big for immobilization. And then another thing to point out on here is that even a single type of material at different times will have a different carbon to nitrogen ratio. So like you have your rye cover crop in the vegetative stage, it's got a much lower ratio than it does once it starts flowering. So if you're thinking about when to till in your crop to time the nitrogen release, that's something to consider. Cardboard, yeah, that would also be very high carbon to nitrogen ratio. Yeah.
Greater than 25 or it's a little more, less than 20.
Well, I think, I mean, if it's greater than 25, it's just going to temporarily tie up the nitrogen. It'll be released eventually. And that could be good. Like if you're not planning to plant your crop right away, like maybe you want that. Maybe you want something to hold on to the nitrogen for a little while and then release it later on when your plant's ready to use it. So it's kind of like this game of trying to match the timing of the release of the nitrogen to when your crop is going to be ready for it. Yeah, and another thing you can do is if you have a really high carbon material and it's close to your crop uptake time, you could just leave it on the surface versus tilling it in, and then it won't affect the nitrogen in the soil so much. But yeah, just something to think about anytime you're adding an organic amendment. Okay, so now I'm going to talk a little bit about plant uptake. Plants really mainly take up the inorganic forms of nitrogen, ammonium, and nitrate. There's some new research that maybe they can also take up some organic forms, but don't worry about that. Ammonium and nitrate, that's what you want to really focus on. So different nutrients are taken up into the plant in different ways. For nitrogen, the main one is called mass flow. And this basically means that the nitrogen is dissolved in the water in the soil, and the plant takes up the water, and the nitrate just kind of comes along for the ride. It's like if you dissolve your vitamin in your glass of water and you drink the water, you got the vitamin with the water. So that's kind of how it is. Nitrogen is extremely mobile, so it can travel to the plant from relatively far away. And then other ones are less mobile, but we'll talk about that in a minute. The phosphorus. So yeah, they use mainly the inorganic forms. And another thing to know is that they don't take up all the nitrogen that you put down. In fact, it's usually not much of what you put down. 78% I think is pretty high. It's usually a lot less than that. So that's not ideal, but again, it does give us room for improvement. Of course, all of that nitrogen that's left in the soil then becomes prone to being lost to the environment. And talk a little bit about those pathways now. I know this was touched on earlier. There's basically four main loss pathways: volatilization, runoff, denitrification, and leaching. And of those four, volatilization happens mainly in hot and dry weather, and the other three all happen in wet weather. So most losses of nitrogen happen in wet weather. Volatilization is kind of a special case. And also of these four, all four of them can be relevant, can dominate in different situations, but kind of on a grand scale, like a regional or a national scale, leaching is the main pathway for nitrogen loss. So I'll talk a little bit first about ammonia. So this is, again, when ammonia gas is released into the atmosphere, it happens when there's hydroxyl ions, which you may recall from earlier means that there is a low pH, a high pH, a low acidity. So yeah, if the soil pH is high or if the manure pH is high, then you're going to be more prone to ammonia loss. But it can happen with any kind of fertilizer that contains ammonia, which includes manures and also includes nitrate. Not nitrate, urea is a big one. Nitrogen losses from farms generally are significant enough that they represent a major economic loss to the farm. The amount of nitrogen you're losing is significant to your bottom line. So it's not only helpful to manage them from an environmental standpoint, it's also like helpful for the farm's economic standpoint. And it changes, ammonia loss in particular changes the nitrogen to phosphorus ratio of your manure, which makes it more challenging to manage your manure. And the things that exacerbate, that make ammonia volatilization worse are basically the same things that you might think of that make water evaporation happen more. So anything that makes water evaporate will also make ammonia evaporate. So like if it's hot outside, or if it's really windy, or if it's really sunny, those things are all going to worsen ammonia loss. And then conversely, if it's raining or drizzly, if the humidity is really high, that's going to be good for reducing ammonia loss. And then, as I mentioned before, the acidity is also important. So that's why you sometimes hear about people acidifying manure to reduce ammonia losses. So other things to know about to reduce ammonia loss. Usually if you're applying manure, most of the loss happens really fast. It happens in like the first couple of days. So that chart up in the right is from some research that I did on manure acidification, and the black line on the top, you can sort of see it, is untreated pig slurry, and then the other lines are acidified slurries. But you can see almost all of the loss happened like within a couple of days, and also almost all of the ammonia was lost. So you can lose a very significant fraction of the available nitrogen in the manure. So that's why the state regulations call for incorporating manure within 48 hours when feasible. Yeah, and also if you can modify the time of day when you're spreading, in the morning or the evening when it's not as hot and it's a little wetter. And then the application method also has a big impact. So broadcasting will result in a lot greater ammonia loss than, say, injection or band spreading or something like that. So the other big form of gaseous nitrogen loss is denitrification. And ammonia volatilization, of course, is the way that you can lose ammonia to the air. But you can also lose nitrate to the air because that's, yeah, because of course you can. So denitrification, or the loss, is the transformation of nitrate back into that stable N2 gas that most of our atmosphere is composed of. And it's also a two-step process. You can get significant production of nitrogen nitrous oxide along the way, which is also a really terrible air pollutant. So you don't want that. Normally, that's pretty minimal, but it depends on the kind of the water content of the soil. So denitrification happens basically when soil is saturated. Because you can see basically what happens is in a saturated soil, there's not enough oxygen. And so the microbes, they really need some oxygen. So they're like, oh, check out that oxygen in the nitrate. I'm going to get that. So they break down the nitrate into nitrous oxide and then they do it again. And then they make nitrogen gas. So yeah, it happens when the soil is waterlogged. And I know we already saw this before, but you can see it where there's been a wet spot in the field. Some of that damage may just be from the plant not having enough oxygen, but some of it is nitrogen, an induced nitrogen deficiency from the lost nitrogen gas. So ways that you can avoid this include improving drainage and then sort of trying to delay your nitrogen application on wetter areas so that it's more closely matched with the crop uptake time, and then also to split it when possible. So that if you lose some earlier, you can still go back and put more on later. Okay, so those are the two gaseous loss pathways for nitrogen. Now we're going to talk about the big one, which is water, which is leaching. And leaching, the form of nitrogen lost through leaching is nitrate. Nitrate is super mobile and it likes to stay in the water. And again, nitrogen leaching can be a pretty significant economic loss to the farm. It's a problem for the environment, but unlike a lot of the other issues that we think about, this one also has a human health implication because if it leaches and you're on well water, depending on what your aquifer situation is, it can sometimes leach into your drinking water, and that's really bad for your health. So you really don't want that. Okay, so this is also a refresher from this morning, thinking about why nitrogen is prone to leaching loss but not ammonium. It has to do with the charge on those two molecules. Remember, nitrate is negatively charged, ammonium is positively charged, and the net charge in most soils on the soil particles is negative. So the ammonium will happily stick around and sorbed to that soil particle and stay put. But the nitrate does not want to stick to the soil and it stays in solution and it basically just goes wherever the water goes. So yeah, so the things that can set you up for big leaching losses of nitrogen include big one-time applications and also the timing of your application. So if you apply it really early before the crop is going to need it, you put this big load of nitrate in the soil. It's just got to sit there waiting for the crop. It doesn't mean that you're necessarily going to lose it, but if you do get a big rain, it's kind of like loading your bases. You got everything set, it's primed, and then you get the big rain and it's all done. So yeah. So yeah, very, very rainfall driven. And these are just some photos kind of showing the three different water-driven pathways of nitrogen loss. So you can have leaching, you can have runoff. This is a photo from Western Maryland. And then you can have denitrification in saturated soil. So to kind of summarize all of this, as with all nutrients, soil pH is really important. For nitrogen, it's a little bit different from some of the other ones because it has more to do with the effective pH on the microbes rather than the element itself to some extent, but anyway, it's always important. pH is always important. And the timing and the rate of nitrogen application are especially important. And then, of course, incorporation of manure when possible. Yeah, okay, so concluding thoughts. Obviously, nitrogen is complicated, and that is the challenge. And another challenge is that, like we mentioned earlier, you can only test for it in your soil at one moment in time. And your test will be accurate for that moment, but 2 weeks later, it might not be the same. So that's a big challenge. But like I said before, there's big room for improvement. We have a lot of opportunity to improve nitrogen management. Split application using a PSNT pre-sidedress nitrate test is an easy one. That helps a lot. And like I mentioned before, making sure you account for the nitrogen credits being provided by whatever was there before. That's also really important and can save you money. Okay, so that was nitrogen. Now, next we'll talk about phosphorus. Don't worry, phosphorus is much less, it's much more boring. There's not as much going on with phosphorus. That's why I study nitrogen. Yeah, phosphorus is cool too. Okay. So it's a lot simpler. It doesn't have any gaseous forms. That makes it much simpler. In Maryland, of course, we tend to have a problem with too much phosphorus rather than too little, but you do sometimes see phosphorus deficiency in crops in Maryland. All of the other crop deficiencies usually present as a yellow or brown color, but phosphorus is different. It's almost always purple. So if you see this purple color, that's usually phosphorus deficiency. Very easy. It's much easier to diagnose than the other ones. So yeah, we'll talk a little bit about phosphorus cycling, phosphorus uptake, and how to manage phosphorus in fertilizer and mineral. So unlike nitrogen, where most of the nitrogen is in the atmosphere, most phosphorus on Earth is found in rocks. And so in natural soils, it's sort of weathered how the rocks like very gradually break down and release phosphorus over eons. But we've accelerated that process by mining some of those rocks. And so today, a lot of the phosphorus in our agricultural fields is found in organic form. The remainder is in inorganic forms, often complexed with iron, aluminum, and calcium. And then, as with nitrogen, some of these interactions are driven by microbes, but not as many. It's not quite as biologically driven. So here's a schematic of the P cycle, phosphorus cycle. You can see the soil solution in the center. That's what we're most interested in. That's the phosphorus that's plant available, and it's in this negatively charged anion form. It can have different negative charges, but mostly just it's PO4 negative, or 2 negative, must be. And that fraction, the fraction of phosphorus in your soil that's in that form is so teeny. It's like a teeny little percentage of all the phosphorus in your soil. It's so small. So yeah, thinking about all the different sources of phosphorus that you can add to the field up here. Then we have loss pathways in blue. Then we have the organic phosphorus fraction down in the corner, and that's kind of undergoing the same mineralization and immobilization reactions that we talked about with nitrogen. So the microbes are going to take up inorganic pee and they're going to release it again when they die and are broken down. But unlike nitrogen, we also have this big non-biological component for phosphorus going on over here. So some of it is, so this is something that's a little confusing. With nitrogen, we talked about nitrogen fixation being the process of making unavailable nitrogen into available nitrogen. That's nitrogen fixation. But phosphorus fixation is the opposite. These guys obviously do not talk to each other. So like phosphorus fixation is when you take available phosphorus and convert it into unavailable phosphorus. I'm sorry, I was not responsible for this. So that's just how it is. But so phosphorus fixation can happen in different sort of levels of being fixed. So there's sorption, which is this sort of lightly held kind of fixation that we talked about earlier that happens for basically all of the nutrients. But then there's also this other process called precipitation that's a little bit of a stronger bond. So with precipitation, the phosphorus combines with iron and aluminum to form these really tightly bound insoluble compounds. That's what happens in humid parts of the country with acidic soils, like where we are. If you go out west, the same thing happens, but with calcium, or I guess also in high tunnel production, anywhere where you have a high soil pH. And those, they're not held there forever, but they're pretty inaccessible. And I know we already mentioned this before, but pH is so important for phosphorus. So this is the green area at the top is like the percentage of the phosphorus that the plant can access. And you can see it's really maximized in this 5.5 to 7 zone. Once you get above or below that, it's really going to be tied up and you won't be able to get it. Okay. So the phosphorus loss pathways are also a lot simpler than for nitrogen. We still have surface loss. That includes erosion, where the phosphorus is attached to a soil particle and the soil particle erodes. And then you can also lose dissolved phosphorus. So if you have a tilled system, you're probably going to lose more phosphorus by erosion. If you have no till, you're going to lose more in dissolved form, but either way. Subsurface loss of phosphorus is really, it happens, but it's usually not really a big deal except in certain really sandy soils, or sometimes in tile, but usually not a big deal. So yeah, phosphorus loss generally is dominated by surface runoff, as opposed to nitrogen loss, which is generally dominated by subsurface runoff. Okay, so talk a little bit about phosphorus uptake. This is the same diagram that we saw before. Nitrogen moves mostly in water. Phosphorus is much less mobile. So phosphorus mostly moves by this process called diffusion, where basically what happens is the root is pulling all of the phosphorus in the zone right around the root. It's pulling it out of the soil and taking it elsewhere in the plant. And so that creates this kind of vacuum, this phosphate-free zone right around the root. And the other phosphorus a little further away, like kind of wants to even that out. So it's going to sort of move on its own towards the root. And Does that make sense?
Yeah.
Okay. Okay. Um, yeah, and the diffusion process is much slower and it's much shorter than mass flow. So phosphorus can't really move very far. But I'll talk about that more in a second. So plants have all these different strategies to help take up phosphorus. They can grow more roots. They can make partnerships with mycorrhizal fungi who will help them collect the phosphorus in the soil. They can also put compounds into the soil that are like organic acids that we mentioned before that help liberate some of the phosphorus. So those are some of the plant's strategies. If they don't have enough phosphorus, they will invest in a lot of those strategies. If they do have enough phosphorus, they will not do those things. They're smart. They don't want to waste energy on something they don't need. And if they have too much phosphorus, they actually have to spend energy to like get rid of the extra phosphorus in the soil. So they're always trying to maintain it at kind of this constant healthy zone. Okay, next we'll talk about phosphorus fertilizer. So I mentioned that most phosphorus in the world is in rock form. So this in particular, it's concentrated in this kind of rock called rock phosphate. And there's just a few places in the world where rock phosphate exists. We're lucky here in the United States, we have a lot of rock phosphate in Florida. So we have a pretty substantial domestic phosphate production. A lot of countries in the world are not so lucky. But actually, most of the remaining phosphorus in the world is in Morocco, which is why the Global Phosphorus Institute is there. So yeah, we have some in Florida for now. We may not have that forever. So part of the reason why it's important to think about using phosphorus responsibly and not using more than we need. Thinking about how to recycle it. So there's all these different kinds of phosphorus fertilizers. They're basically all derived from rock phosphate with different treatment methods, and they have different availability over time. Some of them are more immediately available, and some will be released on a longer time scale. And this is what I was mentioning before about the availability of phosphorus when you add it to soil. So this chart shows, let's see, it's showing the availability, the concentration of phosphorus in the soil. And the different lines are showing the change in availability over time. So the top line is right after you apply, and then the bottom line is like a month after you apply. You can see over time, the availability is going down after you put that phosphorus down. And then on the x-axis, you can also see that availability goes down the further away you get from the granular fertilizer. So once you get about an inch away from where you put it down, it's pretty hard for the plant to get it. And this matters more, when the plants are really small. When they get a little bigger, they can kind of manage and use some of those foraging strategies that we mentioned. Okay. So this is just kind of a different diagram of the same thing, but the practical management implication of this is that if you're putting down phosphorus fertilizer, you really want to, like the placement of phosphorus is really important in a way that it's not as important for nitrogen, because nitrogen can move around, but phosphorus can't really. So you want to put it as close as you can to where it's going to be needed, especially when you're putting down, if you're like putting down starter fertilizer. Okay, just a little bit about manure. They're going to talk about this way more tomorrow, but with dairy manures and slurries, the phosphorus is mostly available right away. with litter, with poultry litter, it's available still in the first year, but not as immediate. So it takes a little longer. And then I just wanted to mention a little bit about legacy phosphorus. I think you guys covered this morning a little bit, but hopefully it can it's good to hear it again. I don't know. But we used to have this agricultural system where most farms grew crops and livestock on the same farm, and the manure was tightly cycled back and forth between the crops and manure. Now we have this system where grain is grown in one place, livestock are raised in another place. So we have these accumulations of manure that are so far away from where the grain came from, it's just not economically practical to drive it back to where the grain is. So we have these accumulations of nutrients, both from manure, also from people eating the food, far away from where it's really needed. So it makes it really economically challenging to recycle those nutrients. Again, I think this is also kind of an exciting area of opportunity. I think there's different people working on ways to figure out how to make that more feasible, more economically feasible. And so it would be really cool if we could kind of close some of those loops again and be more self-reliant on our own phosphorus. But yeah, that's just my opinion. Yeah, it also, of course, makes it hard to manage phosphorus in these areas because no matter what you do, there's just still constantly always more phosphorus coming in. So it's just, yeah, it's a management challenge as well. Okay, so yeah, like I was saying, we have these decades of manure application that have led to excessive phosphorus levels. And this is the chart that we use here in Maryland to sort of rate different phosphorus levels. Most of our environmental losses of phosphorus occur in the excessive zone, which is why those soils are regulated and managed differently. You really want to keep your soil in the optimum zone. One thing about phosphorus loss that's a little different from nitrogen again is that phosphorus loss, while it is an environmental challenge, it's usually not, the amounts that are lost are pretty small from an economic standpoint. So phosphorus loss from the farmer's perspective is less, it's not really so much of an economic problem. Whereas nitrogen, it really can be. So yeah, it's just a difference there. Okay, so principles of phosphorus management. Again, pH, pH, pH. The placement is really important for phosphorus. Of course, timing and rate are also important, but placement is especially important for this one. And anything you can do to reduce erosion and runoff on the surface will help keep the phosphorus from leaving your field. And that's it. There's a summary slide at the end. I won't go through all of these. It's kind of just like a cheat sheet for the exam. But let me know if you have any questions. I think that's it. And I think it's greater than 100. Yep. Okay.
Okay. Anything above 100 on the university scale is considered excessive. The regulatory threshold for the phosphorus management tool is 150. That was the regulatory threshold that was picked out that says you have to run the phosphorus management tool when your soils get to 150 FIV.
So according to the regs, it's greater than 150, but in terms of a plan,
According to the regs, greater than 100 is excessive. Regs put a regulatory threshold of 150 that says you now have to do this risk assessment tool of the phosphorus management tool. That's what that is. All right. Everybody have a good safe trip home. Got out a little bit early this afternoon.